Hello world, it's Thorsten here. I've been dealing with assembler for the past 20 years and boy, I can tell you, it is not only needed if you want to do driver programming or if you want to develop compilers. Knowing it helps you to become a better software engineer by being able to look behind the scenes, what's really happening inside of a program that's running on a computer. So if you want, today we can discuss interpreted versus compiled programming languages, assembler versus machine language, and we will also take a look at disassembling a program with the tool object dump. And in the end, we will be able to modify binary code where we do not even have the source code available. If you open your computer, you will find a processor that looks like this here, and you will find RAM that looks like this here. The RAM is basically a giant data dump that the processor uses to load from and save data to. If the processor wants to do some arithmetic calculations like additions or subtractions, it also has some registers and first needs to load the data from RAM into these registers. Only then it can perform the required calculations. The processor also controls the attached devices of your computer. For example, gets input from mouse, keyboard, and sends output to printer, monitor, and much more. As many of you know, there are two types of programming languages: interpreted languages and compiled languages. Python is an interpreted language, and I have here the source code of a Python Hello World program, which does nothing else but print out Hello World. And when I call this program using the Python executable, then it will print out Hello World. But the machine code will nowhere be visible to you. It is different with compiled program languages like the C language. I have here a program in its source code, hello.c, and when I compile it using GCC, like GNU Compiler Collection, and then I get a file. In this case, it's called hello, and I can really execute this file. And it is a binary file. You cannot read it. Let's try to read it. You see it just contains gibberish and does not really make sense to read it like this. When you want to take a look at it, I recommend a hexadecimal editor like Octeta. With Octeta, you can take a look at every file. Let's first take a look at the Python source code here. And then you see on the far left, you see the address. So it starts with 000, blah, 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 0. So the first byte is called 0. And in this case, it is 70 in hexadecimal writing. So it is 70, and 70 in hexadecimal stands for a small p. So here you see the bytes in hexadecimal notation. Here you see the bytes in how they would be printed if they were printable. Not all are printable, and that is a big advantage of Octeta, because also non-printable bytes can be identified. Let me show you what I mean. We have this gibberish file, hello, and we see here the first byte is in 7F, and this is not even writable, so it is symbolized by a dot. Then it is followed by a 4-5 hexadecimal, 4C, 4-6, and that reads ELF. And that signalizes to the operating system that this file is an extended linkable format file. And this is the typical file that can be executed under Linux. And when we now have a look and do a Control F here in the file and say I want to find not the hexadecimal code, but the char hello, then we find that hello world is here in the clear text in this file hello. And we can also modify now this code. We can now say hello moon instead of hello world. And we exit it and save it. And we again call this hello ./hello. And now it greets the moon and no longer the world. So now you may say, Torsten, give me a translation. What the hell does all this sequence of byte mean, and what does the processor really do? And I tell you that is exactly what assembler is for. We have here object dump, which is a file on Linux, which allows you to translate the machine language into assembler. And let me show what it means. I call it, and here I have my beloved carve and you see this here on the right is a bit confusing for beginners, but in the end it's just the same like here, but a bit smaller. So when we want to understand what's happening, we have to know that the program will start at the main routine. So I would usually do Control F main. Actually, I saw it already. So it could have gone faster if I just had gone here. And here I see now again the bytes, which are, for example, F3, 0F, 1E, FA, and these are all instructions in machine language. And it is very, very hard to understand them. So there's a kind of intermediate language, which is assembler. So this is what I call machine language, and this is what I call assembler. This sequence of bytes gets translated into the endbr command. So I don't have the time to. It would be we do it later. We talk later about what endbr exactly does, but it should be clear to you now that we have machine language and that we have assembler, and then we have the C source code. And the C source code is understandable to human beings. Assembler is kind of understandable, and the machine code is not understandable at all. To illustrate this, I have now made a table. Here I have put in the C code, so the code in C programming language. It is always the same. It is printf hello world, does nothing else but printing out hello world. And then I have done the same code in assembler. It is already a bit longer and much harder to understand what's happening here. And then I have done it again in machine language. And one of the things that you should realize is that there are different machine architectures. There's the Intel x64 architecture, which is probably in your notebook when you're watching this on your notebook, and the ARM architecture, which is on your mobile phone and on your Raspberry Pi. And there used to be many, many more architectures like this. But what you should take from this is that if you want to program assembler, then you need to know which machine architecture you are programming for. So this is a big reason not to be programming assembler if you have to rewrite everything from scratch in order to run it on a mobile phone and on a computer and on a web server and on a notebook, for example. So in reality, this is being done by using interpreted languages like Node.js or Python, or compiled languages like C, but not assembler. So we will program in this tutorial in assembler, but it should be clear that you do this only in exceptional cases. For example, when you want to create a compiler or when you are doing driver programming. Another situation where assembler is very useful is when debugging programs. So let's use the GNU debugger, GDB, to debug the hello binary. We say GDB hello, we say break main, so we set a breakpoint right at the main routine. So whenever you start this program, it will immediately run into the breakpoint and lets you observe the variables and where it is standing. We do this by calling the program run. And now the breakpoint has been reached and we are at breakpoint 1. So using the command disassemble, I can find out what the code is and where the program stands. Again, we see this endbr, which we also saw when disassembling the binary using the object dump utility. After the endbr, the program will push the register base pointer, which means it will make a backup to RAM of that register. Then it can override it. Then it puts the stack pointer into the base pointer. And then it loads an effective address. And this effective address will be stored into register AX, which is a general purpose register, and the value will be this here. So let's have a look what it is putting into RX. So you can use the command X to display memory addresses contents. And with enter, we see the memory address content. I don't really understand what's written there, so let's tell it to interpret this memory content as a string using the /s parameter. And here we see hello moon. So the address where hello moon has been written into the RAM is 55 blah 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 604. And that is exactly where the AX register points to. Then AX is being moved into the register DI, data indicator, and then it will be, then 0 will be moved into the register EAX. So also the AX register, we come to this later. And then the operating system function printf will be called. This operating system function will then inspect the AX register, will see 0 is in it. So I'm supposed to print out something. Okay, where is this? What I have to print out? I'm looking into the data indicator, and there I find hello moon, and it will then output hello moon. Okay, we have already said run here in the debugger. It has stopped because of a breakpoint. We say continue, enter, and it outputs hello moon just as it was supposed to do. So this is a bit an overview how to use the GNU debugger. We will get deeper into this. And I understand that we have left out a lot of explanations that are needed. However, just wanted to give you an overview how to use this GNU debugger. And we will dive in deeper later on. Thanks for watching so far, and I'm planning on making some more videos, one about hex editors, where I will describe how to really take a look at the files in your operating system, including all the topics like Unicode and so on, one video about how to use the GNU debugger, and one video about the assembler commands. For example, the endbr command comes to mind. I have not really explained it in this video. Also, why are there so many movements necessary for a simple hello world program to run? And finally, I would like to show how to program your own operating system, or better, how to program your own bootloader for an operating system, because there you will have direct access to your devices and you will not be shielded from your devices by means of an operating system. Let me know in the comments what topics you would like to see most, and any questions, I love to answer them. See you soon. Bye.